Hi everyone, I'm Shouvik. I'm a postdoctoral fellow at the Academia Sinica Institute of Astronomy and Astrophysics, and I'll talk about the status of dynamical dark energy and neutrino masses in 2025. So my talk is based on these three papers um, since September 2024, and all of them were published in the Astrophysical Journal Letters. So as you know, DESI provided the evidence for dynamical dark energy at the level of 2.5 to 3.9 sigma with their data release 1, and in data release 2 this has increased to 2.8 to 4.2 sigma depending on the supernova dataset used. And so this is an 8 parameter model where 2 parameters are for the dynamical dark energy equation of state and the W0WA parameterization, and the other 6 parameters are for ΛCDM, and this point cosmological constant is rejected at more than 2 sigma. Now yeah, in DESI DR2 paper, they showed that even just CMB plus DESI BAO alone can reject the cosmological constant at more than 3 sigma. Now, they tried also different parameterizations, not just the CPL, and what they find is that all of them point to a transition from phantom to non-phantom nature at a redshift of around 0.5. And now, this is all in an 8-parameter cosmological model. Now, they also find that the neutrino mass bound is quite strong in the ΛCDM model, with the bound to be around 0.072 eV with DESI DR1 combined with CMB data from Planck and CMB lensing data from Planck and Atacama Cosmology Telescope. And this bound has even become stronger to 0.064 eV with DESI DR2. And so for normal hierarchy, the minimum mass required is 0.06 eV, and for inverted hierarchy, it is around 0.1 eV. So basically, it seems that in ΛCDM, not only the inverted hierarchy is in a lot of pressure, even the normal hierarchy is in some pressure. And if you actually extend this probability posterior probability distribution and allow for negative neutrino masses, you actually find that it peaks in the negative neutrino mass region. So these bounds actually relax if you allow for dynamical dark energy, but still you don't see the posterior to be peaking in the positive neutrino mass direction, at least in the 8-parameter W0WA CDM model plus sum of neutrino masses. So this problem is due to the omega m problem in ΛCDM, where DESI actually prefers lower omega m than CMB data, and CMB actually CMB power spectra actually constrains this omega c plus omega b, which is the combination of physical densities for cold dark matter and baryons. This CMB peaks constrain this very well, and now if BAO infers the omega m to be lower than CMB, then the omega nu component actually becomes negative, and that is why cosmology seems to be preferring a negative neutrino mass in ΛCDM. Now, this omega m tension is also driving the evidence for dynamical dark energy, and the situation has gotten worse from DESI DR1 to DESI DR2, as you can see. But DESI as internal consistency is okay, because DESI DR2 is completely okay with DESI DR1. So as you can see in this omega mh not RD plane, where RD is the co-moving distance to the drag epoch. Now, neutrinos have masses, and neutrinos, when they become non-relativistic, they count in the matter and matter content, and since they don't cluster easily in because of higher thermal velocities, they actually suppress the matter power spectrum in the smaller scales, and this affects CMB lensing, because the CMB lensing of the CMB photons is produced by the large scale structure, and if there is a suppression in the matter power spectrum, it will reduce the lensing. So CMB lensing potential is correlated with neutrino masses, and now there is this consistency check parameter AL, and which should be equal to 1 if you vary it as a parameter in your model, because then it would mean that you are getting the lensing of the CMB photons actually agrees with the theoretical prediction. But if AL is greater than 1, it means the data prefers more lensing than that is theoretically predicted from the model. Now, there was this lensing anomaly in Planck PR3 or Planck 2018 likelihoods, where they found more than 2 sigma evidence of this lensing anomaly, because AL was discrepant to AL equal to 1 at more than 2 sigma. But the newer PR4 likelihoods actually show that in lambda CDM at least, the tension is less than 1 sigma. But with the helipop likelihood for high multiple power spectra to be the best for as far as lensing anomaly is concerned. But these results are in lambda CDM, and nobody has checked it with dynamical dark energy. We will use this notation A lens instead of AL. Now, there is also Hubble tension, and you can project it as a tension in the RS drag or RD, because CMB prefers a RD value of around 147 megaparsec, whereas BAO and supernovae, they basically constrain, especially BAO, it constrains H naught and the multiplication of this H naught and RD. So BAO gives you hyperbolic contour plots, and BAO is okay with CMB data, and as well as the measurement of H naught from calibrated supernovae, calibrated type 1 supernovae using the Cepheid variable stars. Now, this BAO and the calibrated supernovae give you a value of RD of around 138 megaparsec. So there is around a 7% difference, and this leads to a Hubble tension of around 5 to 6 sigma. And to reduce the tension, what one can do is reduce RD. The Hubble tension can be projected as a tension in the measurement of this RS drag or RD. And one way to reduce this tension is include new radiation species. So what previously used to be done is add NF as a parameter to reconcile the Hubble tension when the Hubble tension was at the level of 2-3 sigma. So if you can add one extra neutrino-like species, so that means the NF of around 4, then you can basically solve the Hubble tension completely. But CMB data, the CMB power spectrum actually gets suppressed as you add more and more NF, and in this way you can actually constrain NF from CMB data, and polarization data is even more sensitive to NF because the peaks in the polarization power spectrum are narrower. So the thing is that it's not possible to solve the Hubble tension with just NF, because now the bound is around 3 plus minus 0.2 in the lambda CDM plus NF model. So but we included in our model just to see how far we can reduce the tension. So our 12 parameter extended cosmological model includes the 6 parameters of lambda CDM, then W0 WA, then simple extensions like NF, sum of neutrino masses, A lens, and alpha S, which is a running of the scalar spectral index. So our main goals are to check whether the preference for dynamical dark energy survives in this largely extended parameter space, especially because W0 WA are correlated with sum of neutrino masses and A lens. We want to provide a reasonable bound on the sum of neutrino masses parameter, which can be used by the cosmological and particle physics community. Especially we want to see, if you allow for extra parameters, if we can get a detection of positive sum of neutrino masses. We want to give a definitive answer regarding the lensing anomaly in the dynamical dark energy scenario with Planck PR4 likelihoods, because in lambda CDM there is no lensing anomaly with Planck PR4 likelihoods. We also want to assess the level of Hubble discrepancy in this 12 parameter extended cosmological model using the new datasets. So our datasets are Planck PR4, which is helipop and lollipop for high L temperature and polarization, and low L E-mode polarization, and we use Commander from Planck 2018 likelihoods for the low multipole temperature. For CMB lensing, we use Planck PR4 and Atacama Cosmologic Telescope data release 6. For BAO, in the first paper we had used DESI data release 1, and for the second and third paper we used DESI data release 2. For supernovae, we use Pantheon Plus and the Dark Energy Survey Year 5. For weak lensing, we use Dark Energy Survey Year 1 data. Note that Pantheon Plus and DES Year 5 have some supernovae in common, so the two datasets cannot be used together to avoid double counting. So our main results in the first paper was that if you add only just CMB data or CMB lensing, then you can you find no proper constraints on the W0 WA parameters. But once you add DESI and supernovae data, then you get proper constraints on these W0 WA parameters. And what we found is that CMB plus BAO plus Pantheon plus actually allows for cosmological constant within 2 sigma, and it also allows for this some part of the non-phantom dynamical dark energy, where it means that the equational state of dark energy remains non-phantom for throughout the evolution of the universe. But DESI-5 data actually rejects the cosmological constant as well as the non-phantom dark energy region at more than 2 sigma. So our main conclusion is that since the Pantheon plus at least allows the cosmological constant within 2 sigma, then this evidence for dynamical dark energy cannot be considered conclusive, and it remains basically dataset dependent. Now, in the next paper, in the second paper, what we found with DESI DR2 is that the conclusion sort of remains same, that the cosmological constant is still allowed at the edge of the 2 sigma contour, and some part of the non-phantom dark energy is still allowed with Pantheon plus combined with CMB plus BAO. So our conclusion sort of remains same. And DESI-5 again showed that it actually rejects cosmological constant and this non-phantom dark energy region for more than 2 sigma. So again, for neutrino masses with DESI DR1, what we found is that all of our dataset combinations actually produced a peak in the positive neutrino mass sum range, which is a quite strong result, because nobody has seen this kind of behavior before with simple extensions. And but we didn't get a 2 sigma detection at that time. And so this was with the DESI DR1, and we found a bound of around 0.3 eV during that time at 2 sigma. Now, with DESI DR2, the things got a bit worse, actually. So with CMB plus BAO, we see a clear peak, but with CMB plus BAO plus Pantheon plus, we actually don't see a peak. And if you extend this, you will get a peak in the negative neutrino masses. But CMB plus BAO plus DESI-5 actually showed peak in the positive neutrino mass region. Now, if you use the weak lensing data with it, then you see actually the first 2 sigma detection of sum of neutrino masses, and we got this bound of 0.19 plus 0.15 minus 0.18 at 2 sigma. And even with Pantheon plus, instead of DESI-5, we get a 1.9 sigma detection. So this is very promising, because weak lensing data actually prefers slightly lower S8, and that actually leads to preference for higher neutrino masses, and I will discuss this later again. But the thing is that this detection of some neutrino masses is possible in this extended model because of the weak lensing data, as well as the inclusion of the A lens as a parameter. Now, we also see a lensing anomaly in DESI DR2 when we include the weak lensing data. So when we don't include the weak lensing data, CMB plus BAO plus supernovae give a result which is okay with A lens equal to 1 at less than 2 sigma, but it's actually a bit discrepant at more than 1 sigma level. Now, if you add weak lensing data, then the parameter degenesis lead to A lens equal to 1 being rejected at more than 1 sigma. So this is, again, for the first time we show that the existence of the lensing anomaly can depend on non-CMB datasets, even with Planck PR4 likelihoods. Now, in case of Hubble constant, we find that there is no proper constraint with CMB or CMB plus lensing as long as you have dynamical dark energy, because W0 WA are very correlated with H0, and then if you add BO data, you start to see some constraints, and only when you constrain the W0 WA parameters with supernovae data, and then you can actually see the proper constraint on H0, because the supernovae data actually breaks this degeneracy between W0 WA and H0. So Hubble tension we saw is still persists at the level of 3.2 to 3.9 sigma with DESI DR1 when we use CMB plus BO plus supernovae, and with DESI DR2 we saw that this increases to 3.6 to 4.6 sigma, so 4.2 sigma. So DESI DR2 actually increases this tension in this extended model. So the Hubble tension is robust when compared to, in contrary to the case of dynamical dark energy, for which the evidence actually does not survive evidence for dynamical does not survive when we add simple extensions to the W0 WSCDM model. Now, for S8 tension, I would like to mention is that with DS year 3 weak lensing data, this tension is actually reduced to 1.4 sigma with CMB plus BAO plus supernovae, and this is due to the Planck PR4 likelihoods, because with Planck PR3 this tension was 2.4 sigma, and what the Planck PR4 likelihoods had previously already shown that even in ΛCDM, this tension with the dark energy survey year 3 weak lensing data is reduced to 1.5 sigma. So adding extra parameters is actually not reducing the tension. It's mostly that the Planck PR4 likelihoods are prefer lower S8 than Planck PR3. Now, for NF and alpha S, we actually don't see any deviation from expected standard values. I want to mention a few degeneracies of some of the masses, and those are there is a strong degeneracy with the WA parameter, which actually controls the evolution of the dynamical dark energy in the late time, and both of them, sum of masses and WA, actually affect the evolution of the universe at late time, so they are correlated. ALNs and sum of masses are correlated because of the effect of sum of masses on the CMB lensing, and S8 and sum of masses are negatively correlated because sum of masses actually leads to stronger suppression of the power spectrum, and that means it decreases S8. So higher sum of masses corresponds to lower S8, and since the weak lensing data prefers lower S8, it chooses higher sum of masses. So that is why we get a detection of sum of masses with the weak lensing data. But inclusion of the ALNs parameter is also very important for the detection, because without the ALNs parameter, we don't actually see any detection. Now, I would briefly like to mention the non-phantom dynamical dark energy case. So if you restrict the parameter space only to the non-phantom dynamical dark energy, because this corresponds to the parameter space of quintessence, which are single scalar field models to describe dark energy. And these are well motivated from quantum field theory. And so if you restrict this parameter space to non-phantom dynamical dark energy, then what we find is that with CMB plus BAO plus supernovae, the lensing anomaly is already more than 2 sigma, and if you add weak lensing data, then it goes over to more than 3 sigma. So restricting the parameter space to quintessence like or non-phantom dynamical dark energy, which is more realistic than a phantom dark energy, but if you have that, then you also need to explain the 3 sigma plus lensing anomaly. So this was the result of the third paper, the main result of the third paper. So in summary, the evidence for dynamical dark energy component is not yet conclusive and remains dataset dependent. We got the first 2 sigma plus detection of non-zero positive neutrino mass sum, and hopefully we see a future 5 sigma detection. We recommend this bound of around 0.2 eV for to be used by cosmology and particle physics communities as a reference. And the lensing anomaly with weak lensing data suggests for the first time that the existence of the lensing anomaly could depend on non-CMB datasets, even with Planck PR4 likelihoods. Simple extensions to the ΛCDM model explored in this study are insufficient to resolve the Hubble tension, and S8 tension with the weak lensing data is actually not a big tension anymore, and it is much less than 2 sigma basically. With DESI DR1, since the error bars are slightly larger, this is actually close to 1 sigma, not even 1.4 sigma. And restricting the parameter space to non-phantom dark energy leads to a 3 sigma plus detection of lensing anomaly. So if you want the dynamical dark energy to be non-phantom, to be explained by single scalar field theories, then you also need to explain the existence of this 3 sigma plus lensing anomaly basically. Thank you.